Hey, can't you hurry up? We're getting late. The rest of the class are probably already at Miss Chan's house, having the party and starting to eat.
I am hurrying. Be patient. Wait, is this the house? Look,
Wow, your picture is weird. It looks like a haunted house. Is this it?
look.
Number 13 on Einstein Road. Should be this one.
Isn't this Miss Chan's house? How come it is an old granny receiving us?
Well, Miss Chen is allowed to have family too.
Yeah, right.
Hi, Granny. We're here to visit Miss Angela Chan.
It feels really creepy here. The lights are off. It's like a haunted house indeed.
I only feel that it's really cold here. The wind is chilling.
Gosh, someone's moving there.
Really? Maybe just your imagination?
Go! Hey, do you think the granny is dumb? She isn't talking at all.
Well, it's not really our business. Oh, have we come to the South Pole? How come it's so cold here?
Oh, here's a thermometer. Let's see what the temperature is. No way. 53 degrees? It's cold like an icebox here. How can there be 53 degrees? The highest recorded temperature is only 56.7 degrees, which was recorded in July 1913 in California in the United States. Surely this thermometer is broken.
Oh, come on. We should really take you for an eye test. Look, what does it say?
Right, it says 12 degrees. Then why does it say 53 here?
Okay, let me ask you. What's the normal temperature of the human body?
98.6 degrees for sure. You have a fever if it goes above 100 degrees.
Okay, then at what temperature does water boil?
Well, even primary school kids know it. Water boils at 100 degrees.
So, is it the same temperature when a person has a fever and when water boils?
Surely not. How can that be? If we're hot like boiling water when we're having a fever, we should be dead.
So you're not that dumb after all.
Oh!
We use temperature to reflect how cold or how hot an object is. The most common measurements are Celsius and Fahrenheit. These are their respective symbols, like this and that. Celsius and Fahrenheit are two different scales, just like we can use centimeters or inches to measure the length of an object. Just now you saw that the thermometer read 53 degrees. That is Fahrenheit. When it is converted into Celsius, then it is 12 degrees. As for body temperature, normally it is 98.6 degrees Fahrenheit or 37 degrees Celsius. If you have a fever that is 100 degrees Celsius, you would have been long dead from overheating. Look, there's even a garden here. Oh, wait. How come there seems to be some light from a flame? There isn't anybody in this house. Who could have lit the fire?
It looks ghostly.
That's no ghost. I just thought I'd set up a barbecue since you seem so cold. Look how frightened you are.
Well, you never talk, so we thought you couldn't.
Silence is golden. It doesn't mean I'm dumb. Are you much warmer now?
Of course, it's quite toasty by the fire.
How did you two manage to find this place?
Miss Chan gave us this strange photo. We followed it and found this place.
Oh, this is a thermal image, also called a thermogram. The different colors correspond to different levels of heat emission. The hotter it is, the redder. The colder an area, the bluer. Have a look here.
Wow, that's true. The stove is very hot, so through the thermographic camera, it appears red. The barbecue fork is less hot, so it appears yellow. There's a red cloud behind Andrew. Oh, I see. Andrew, you are farting. The thermographic camera shows it as red, so it must be hot.
Although we can't see it with our own eyes, oftentimes we can feel the heat emitted from an object. This process of heat moving from one place to another is called heat transfer. There are three mechanisms of heat transfer. They are conduction, convection, and radiation.
See, we're now sitting by the fire. Even without touching the fire directly, the heat of the fire is transferred to us to make us warm. This kind of transfer is called radiation. The heat of the sun is transferred to the surface of the earth by radiation too.
Objects of high heat radiate their energy in all directions. If our temperature is lower than these objects, then when we absorb their radiation, we feel warm.
So all matter has a chance to absorb or emit heat through radiation?
Yes, but different materials radiate and emit in different degrees. Let's do an experiment. First, let's find two flasks. Let's paint one black and the other silver. Then, we put a thermometer in each one. Now, we put them at equal distance from the fire. Okay, now the experiment begins. At the moment, the black flask measures 26 degrees Celsius, and the silver one also 26 degrees Celsius. We wait 10 minutes. Then, we look at the thermometers again. The black flask is now 44 degrees Celsius, and the silver one, 37 degrees Celsius.
The temperature of the black flask has risen more.
So it means that the black flask has a high capacity to absorb radiation, and the silver one has a lower capacity.
That's a good deduction. Let's do another experiment. This time, I put hot water of the same volume and at the same temperature in each of the two flasks. For each flask, I seal it with a rubber stopper with a thermometer installed. I now begin the experiment by taking note of the temperature of the two flasks at the start. We wait 10 minutes. Now, we read the thermometers again. The temperature in the black flask is 44 degrees Celsius, and the temperature in the silver flask is 48 degrees Celsius.
The temperature of the water in the black flask has dropped down more.
The faster the water transfers its heat, the more the temperature drops.
It means that the black flask is more capable of radiation and the silver flask less radiative.
The results of the experiment show that materials that are black are good for both absorbing and emitting radiation.
And objects of silver or light colors are not ideal mediums for either absorbing or emitting radiation.
That's why we wear light-colored clothes in the summer. They absorb less radiation, making it less hot. On the contrary, wearing dark-colored clothes in the winter makes us feel warmer because dark surfaces absorb radiation better. If I put 2 pieces of ice of equal size under the sun, one covered with a piece of white cloth and the other with a black one, which piece of ice do you think will melt faster, and why? Heat is transferred in other forms aside from radiation. Here I have a metal stick. With some wax, I've attached paper clips to it at various locations. Now, I'll heat up one end of the stick with fire. Can you guess what will happen?
The clip closest to the fire will fall off quickly.
And the clip farther from the fire will fall down last.
So, how do you think heat is transferred in this example?
Obviously, it's transferred from this end. Is this conduction?
Conduction can take place within an object and also between 2 touching objects. In the paperclip experiment just now, when the metal stick is heated, the heat is transferred through conduction from the hot end to the cold end. During this process, the heat is also transferred to the wax along the way, melting it and making the paperclips fall off one by one from that end.
Ouch! Oh, hot. It burns.
Why would anyone hold a metal cup this way? A normal person would hold its plastic sleeve. Of course, you will be burnt if you hold it by its metal part.
Huh? Why?
Let me show you something. Here I have several spoons made of different materials: wood, plastic, silver, and stainless steel. I put a lump of butter at the same height on each spoon, then I put them in a clear container with hot water. Can you guess what will happen?
The butter on the silver spoon has melted very quickly.
The stainless steel spoon wins second. The butter on the wooden spoon and the plastic spoon is taking a long time to melt.
What do you think affects the melting speeds here?
The temperature of the spot where the butter is stuck.
Then what factor decides how hot the spot is?
It is how fast heat is transferred to where the butter is.
So it means that the 4 spoons have different capacities in conducting heat.
Absolutely. Different materials conduct heat differently. You just saw that the butter on the silver spoon melted the quickest. It is because it conducts heat most easily. Metals in general, like silver, bronze, iron, conduct heat quickly. They conduct heat better, and we call them good conductors of heat. The butter on the wooden spoon and the plastic spoon does not melt readily because the conductivity of these two materials is not so good. Generally, materials that are not metal conduct heat slower. They have a lower conductivity. We call them poor conductors of heat, or insulators.
The spot that burned you just now is made of metal. It has a high conductivity. That's why it is so hot. The sleeve is made of plastic. It has a low conductivity. That's why it's not so hot, and you won't burn yourself if you hold it there.
In fact, many of our household goods are either made with good conductors of heat or poor conductors of heat.
So, now you know there are good conductors of heat and poor conductors of heat. Which do you think air is?
I know how we can find it. Are there any matches?
Wow! Even though the match is so close, it doesn't catch fire.
This is because air is a poor conductor of heat. It is hard to conduct heat through air to the match. Therefore, the match is not hot enough to burn.
Ah, this young boy is pretty smart, huh?
Oh, Granny, it's me. I said that. It's me.
Air is a poor conductor of heat, which is important for many animals. Some animals, like the polar bear, can live in very cold places because its thick fur traps air, which helps keep it warm.
I see. So that's also how winter clothes work. A down jacket is warm because it stores a lot of air in it, which helps to stop heat from dissipating.
That's great that you understand this. This house is very cold at night. Now, don't say that Granny is mean. Here is a pile of newspapers. Should you be cold tonight? Help yourselves.
No, you don't mean it!
Here are 2 jackets. They are of about the same thickness. One has a lining that is rough and uneven. The other is all smooth. Which would you choose to keep warm and why?
Wow, it's freezing cold here. Oh, I see. The air conditioning is on, blowing some real cold wind on us. No wonder why it's so cold.
Then quick, go turn it off. I know. Can we switch it so that it blows warm air?
I don't even know where's the remote control.
Then go find it.
Where is it?
It's okay. I've turned it off. Why should you be scared? The old granny is just being nice. She's afraid that you might get cold, so she's brought you a heater.
I had thought you really wanted us to use layers of newspapers to trap air, so to keep ourselves warm.
Wow, now the whole room is warm. That's cozy.
By the way, why do people install their air cons high up on the wall? It is so troublesome to have to find a remote control each and every time. But the heater normally sits on the floor.
Here, I have a glass ring filled with water. Now I light an alcohol burner at its left bottom corner. Then I put a purple granulate in. See how the water moves inside the tube?
I see it! The purple granulate is dissolving in water, so we can see the water flow clearly. The water close to the burner rises up, and the water on the other side of the ring sinks down.
So, on the side that is hot, the water goes up. On the side that is not so hot, the water goes down.
Just now, I heated the water so that you could see how it flowed. This time, I am going to heat up some air. Pay attention and see if it acts any different.
I bet that the smoke near the candle will go up, and the smoke on the other side will go down.
Bingo! The smoke shows us how the air flows. It means that hot air rises, and air that is not so hot sinks down.
So in both cases, the heated goes up, and the cold goes down.
Indeed. When I heat the glass ring on the bottom left corner, the water goes up as it gets heated. At the same time, the cold water in the tube goes down to fill the space where the hot water was. The water flows in a circular way so that eventually all the water in the ring will become hot. In fluids, heat transfers in a circular manner from one place to another. This is called convection.
So there is convection in air too. In the candle experiment just now, we saw that the smoke was moving in this manner. The air above the candle went up after being heated, and the cold air around it went down to fill the space where the heated air was.
Convection can happen in both liquid and gas. The heating element in this electric kettle is installed at the bottom so that water can be heated through convection more effectively.
So when we install an aircon high up on the wall and put a heater on the floor, we're using the principle of convection.
Oh, so now I understand why those promotional videos tell us that when there is a fire, we should crawl on the floor to safety instead of by walking upright.
Is that relevant?
Oftentimes, those injured in a fire are injured by breathing in too much smoke, which puts them into a coma or shock. During a fire, the smoke goes up following the hot air. Therefore, there is less smoke near the floor. So if you crawl, there is a bigger chance that you can survive. Hey, you two, watch this closely. Make sure you don't blink.
Why is it swirling?
Right, why? Can you use the principle of convection to explain why this paper spiral would turn? Why?
Why are you guys here? When do you come?
Since a long time ago. It was just that you two were so late, we decided to make a joke on you.
So Granny, you really are Miss Chen.
Don't be angry. I'll go fetch some drinks from the fridge, okay?
Nice!
This drink in carton packaging and this drink in an aluminium can have been in the fridge for the same period of time, so their temperature should be the same. But how come the can feels colder to the touch? This also has to do with the transfer of heat. Try and see if you can solve the puzzle.